So we'll start at example 14 with the assumption that you guys can remember whatever that we have covered so far in the chapter of factors so far. Okay, example 14 part A is a quite popular question in the past year. Show that two lines are skew lines. But to show that two lines are skew, there are two conditions to establish. You have to show that they are not parallel and they don't intersect. Okay. Skew lines means not parallel and do not intersect. But earlier in example, I think it should be example 11. In example 11 on page 15 earlier, we have done before on how to show that two lines are not parallel. No, I think it's not exactly that thing. Okay, maybe let me go back to example 11 for a while. Okay, in example 11, under method 1, we have tried to show that the vector connecting A to B is not parallel to line L1 and L2. Okay, so coming back to here, to show that two lines are skew, the first thing to establish is that the lines are not parallel, and we are going to do something similar. Okay. Now, to show that the lines are not parallel, just look at the direction vectors. Okay, so these two direction vectors, we only need a statement. When we show that two vectors are not parallel, our syllabus doesn't require us to show by computation. They only need us to state a sentence. A sentence form will do. Okay. So as I mentioned before in the previous lesson, if you want to compare two vectors and you want to verify that they are not parallel, one easy way is to make if you have like 1, 2, 3 and 1, 3, 4, where the x components are the same and the yz component are different, then of course these two vectors are not parallel. This one we can tell easily. Okay. Now, if you look at these two green colored vectors, the two direction vectors, they have nothing in common. They have nothing in common. Right, so you can actually notice that the 7, 5, 1 is actually the same as 7 followed by 1, 5 over 7, 1 over 7. You just factor out the 7. Okay, so when we factor out a scalar coefficient, the direction remains the same. Right? And after you factor out, right, notice that now the x components are the same. Right? So for example, if I call this vector B and I call this vector C, right, B and C are actually having the same direction. Right? B, C are actually having the same direction. Right? And we know that A is not parallel to C. A is not parallel to C because A and C have the same x component, but the yz component are different. And so if A is not parallel to C, A is of course also not parallel to B because B and C have the same direction. And so this is a logic that we are going to use here. Okay. So the idea is just to make one of the components to be the same so that you can easily compare. Right, so you can just write 7, 5, 1 is equal to 7, 1, 5 over 7, 1 over 7. And then once you have this, it should be clear already. It should be clear already, and you don't really need to say much. Our syllabus doesn't require you to say much. And so, yeah, maybe we can just say, note that 751 is equal to 7 times this vector. Right, so, 1, 1, 1 is not a scalar multiple. Sorry, I mean 1, 1 minus 1. Yeah. 1, 1 minus 1 is not a scalar multiple. Of 7, 5, 1. Or you can also say it the other way around. It means the same. You can also say 7, 5, 1 is not a scalar multiple of 1, 1 minus 1. Therefore, the direction vectors of L2 is not parallel to the direction vector of L1. Then we can say the lines L1 and L2 are not parallel. This is just to establish that the lines are not parallel. So not much computation needed. They just expect you to state in sentence form. Stating that one vector is not a scalar multiple of the other. Then mention that the direction vectors are not parallel, therefore the lines are not parallel. Now, this is the first condition established. Now we need to establish the second condition, which is the lines do not intersect. The lines do not intersect. Okay. So to verify that the lines don't intersect, you need to follow the procedure. You need to follow the procedure which we learned on page 14. And the procedure to check whether two lines are intersecting, we'll follow that procedure. Okay. So in our working, we say equate the equations of L1 and L2. And then you have this 1 plus lambda, lambda, and 1 minus lambda. And the other side will be in terms of min. And then write down the three equations, labeling them as 1, 2, and 3. As usual, I prefer to move the constant terms to one side first so that the thing becomes simpler. And now I call this equation 1. This one is simple enough, I call it equation 2. This one I move it such that minus lambda is minus 2 plus mu. Call this equation 3. Okay. Then pick two of the three equations to solve. Pick two of the three equations to solve. Here I pick 1 and 2. You can also pick a different pair. Whichever two that you pick, make sure not to touch the one that you don't pick. When you solve for lambda and mu, just use the two equations that you pick. Don't touch the third equation that you didn't pick. Okay. So here I pick 1 and 2. Solving 1 and 2. 1 and 2 happen to have the same left hand side, so we can conveniently equate them. 7 mu is equal to 2 plus 5 mu, which means 2 mu is equal to 2, which means mu is equal to 1. Sub mu equals to 1 into either equation 1 or 2. Into equation 1, that would be convenient. Lambda is 7 times 1, that means lambda is 7. And then use the third equation to perform checking. And so we always follow this procedure, and we have done something similar before this. So check whether the two values for lambda and mu that you get satisfy equation 3. Okay, so you compute your left hand side of equation 3 and right hand side of equation 3 separately. Left hand side of equation 3 is minus lambda, according to our equation 3 above. So it's minus 7. Right hand side of equation 3 is minus 2 plus mu, which is minus 2 plus 1, which is minus 1. And so these two are not equal. And you can choose to write not equal to minus 7 here to make it more obvious. Okay, then you conclude, since left hand side of 3 is not the same as right hand side of 3, mu equals to 1 and lambda equals to 7. Do not satisfy equation 3. Okay, therefore, the system of equations 1, 2, and 3 is inconsistent. And when we say a system of equation is inconsistent, that means we cannot find any pair of values lambda and mu that can satisfy all three equations simultaneously. That's the meaning of inconsistent for a system of equation. And therefore, we can conclude that the lines L1 and L2 do not intersect. And finally, we say, since L1 and L2 are not parallel, and they do not intersect, we conclude that L1 and L2 are skew lines. Okay. Okay, so that's the end of part A. Okay, let's recap the whole procedure to show that two lines are skew. Okay. To establish that two lines are skew, we need to establish two things: not parallel and do not intersect. Okay. So this part at the top in blue color is the part where we establish that the lines are not parallel. Where you only need to say that one direction vector is not a scalar multiple of the other, and therefore direction vectors are not parallel, and because of that, the lines are not parallel. Okay. Then the part in purple here is the part where we show that the lines do not intersect. So we follow the usual procedure. We equate the line equations, form three equations, then pick two out of the three equations to solve for lambda and mu, then use the third equation for checking. Since the left-hand side and right-hand side of the third equation are not the same, then the values of mu and lambda do not satisfy the third equation. And then we say the system of equations of 1, 2, and 3 is inconsistent, which means there is no solution for the system of the three equations. Then we conclude the lines don't intersect. So at the very end, we combine the two conclusions that we had just now. So earlier we had a conclusion that they are not parallel. Then we also had a conclusion that they don't intersect. Then at the end, you combine, since not parallel and don't intersect, they are skewed. Okay. So this is the whole procedure. Usually 4 marks or sometimes 5 marks may be given to show that two lines are skewed. So make sure you know the steps to perform. Okay, for part B, find the shortest distance from point A to line L1. Okay, just simply draw a line L1 to visualize. You have direction vector 1, 1, minus 1 for line L1, and of course A is an external point, then only you can find the shortest distance. Okay, this will be the distance that they want. Okay, to find the shortest distance, we know that we have to first find the foot of perpendicular, and then get the vector AF. The length of the vector AF will be the required distance. Okay. So let's implement the procedure to find foot of perpendicular, which we have done before multiple times. Okay, first is of course to introduce F as a foot of perpendicular. Let F be the foot of perpendicular. Okay, from A to L1. Okay, A has known coordinates. I label it here so that I can refer easily. Okay. First step, F lies on L1. Okay. So OF will satisfy the equation of line L1 for a particular value of lambda. Okay, so we have 1 plus lambda, this is lambda, 1 minus lambda, for some lambda in R. And then next, form the vector AF. OF minus OA. Then just substitute. Hey, wait, it's not this. This is 1 plus 1 is 2. Yeah, that's 2 minus lambda. Then next, notice that the vector AF is perpendicular to the line L1. AF is perpendicular to the line L1. This means vector AF dot with the direction vector of L1, which is 1, 1 minus 1, is equal to 0. Sub in the values. Compute the dot product. It's 3 lambda minus 4 equals 0, which means lambda is 4/3. Okay, what's the aim of this question? The question doesn't really ask for the point f. The question is not asking for foot of perpendicular. The question is asking for shortest distance. Right, so we don't really need to find the point f. We don't really need to find the point f. We are more concerned about the distance af, right, which means this time the lambda equals to 4/3. You don't have to sub into OF because the question doesn't ask for OF. The question only asks for the length of the vector AF. Okay, so this time we just sub lambda equals to 4/3 into the expression for AF. AF will be 4/3, 4/3 minus 2, 2 minus 4/3. Then at the end, we have to mention the phrase shortest distance. From A to L1. It is just the length of the vector AF. And just apply the length formula. Okay, press your calculator and you will get square root of 8/3 units. Okay, the word shortest distance needs to appear at the end. The phrase shortest distance must be mentioned at the end. Surd of 8/3 is not the only acceptable final form. Other equivalent forms are also okay as a final answer. So this one you can also write as surd 8/3. It means the same, which is also the same as surd of 24 divided by 3. They are all equivalent. And that's it for example 14. Okay, for information later, I mean, not today, but a few days later, when we start to do FP1 vectors, there will be a faster way for us to find the distance from point to line. There will be a faster way involving cross product. We haven't covered cross product yet at this stage, but we will learn a faster way to find distance from point to line when we do FP1 vectors. And the method that I'm using here is actually not the fastest way, but it still works. angle between two lines. This is the next page on page 19. Okay. The angle between two non-perpendicular lines is defined to be the acute angle made by the direction vectors of the line. Okay. So first of all, to find angle between two lines, it doesn't necessarily need to be a pair of intersecting lines. Uh, it doesn't necessarily need to be a pair of intersecting lines, because look at the way the angle between two lines is defined in the first sentence here. It says the angle is an acute angle made by the direction vectors of the line. So even if you have two non-intersecting lines, for example, a pair of skew lines, so even if you have a pair of skew lines, let's say L1 like this, L2 like this, and they never intersect, let's say these are skew lines, okay, and you have the vector B1 this way and the vector B2 this way, it is still possible to find angle between them. It is still possible to find angle between these two lines, because it is just defined as the angle between the two. So direction vectors they are vectors, they are free. So of course you can move the vectors around such that B1 goes this way, B2 goes this way, the direction maintained. And now that they are diverging, you can find the angle between them. And so even for non-intersecting lines, you are able to find angle between the two lines, because the angle is just defined as the angle between the direction vectors. Okay. Now, if you look at the formula, the only difference with this formula as compared to the formula we learned earlier for angle between two vectors is that there is a modular sign at the numerator. So if you look at this diagram, right, to find theta, we usually would write cos theta is equal to b1 dot b2 divided by length of b1 followed by length of b2. This is the usual formula that we use. However, because direction vector is not unique, my B2 could be pointing the other way. My B2 could be pointing the other way. It's possible. So if my B2 points the other way, then the angle between B1 B2 will become this big angle here. My theta could be here, possibly here. And if the theta is here, then it becomes obtuse. It becomes obtuse if you calculate it using the usual way. Right, so but the issue is that in the first sentence here, they define angle between two lines to be an acute angle. So to ensure that your answer becomes acute, you just need to put modulus around the numerator. You just need to put modulus around the numerator, and to ensure that the fraction on the right hand side becomes positive. And then when you take cos inverse of a positive number, you will get an acute angle. Okay. Now, for the case of two intersecting lines, it's even easier to understand. Let's consider these two intersecting lines. They intersect at point I, let's say, L1 and L2. Okay. So my B1 could be pointing here, my B2 could be pointing here. Okay. So if B1 and B2 points this ways, as what is shown on the screen, then the angle between B1 and B2 will conveniently be the acute angle that you want to find. This is the acute angle that you want to find. However, if B2 points the other way, then B1 and B2 are diverging. When B1 and B2 are diverging, you get the angle over here. Let's call it alpha here. But alpha is not what we want. We actually want 180 degrees minus alpha according to this diagram, because this is the acute angle between the lines. And so we actually want 180 minus alpha. And a quick way to get 180 minus alpha is just to use the usual formula. And so if you call the green angle, if you call the required angle to be theta, then you just take cos theta to be b1 dot b2 divided by length of b1, length of b2 with a modulus at the numerator. Then you are going to get theta for sure. If you don't put modulus there, you will get alpha, which is something you don't want. But once you put modulus there, you will get theta for sure. Okay. Right. And this is actually the formula that is printed for you in the box, in the notes. Right. So it's just presented in a different way where they move cos over to the right hand side, but it's the same thing. Right. It's actually cos theta equals to b1 dot b2 over the length of b1 and the length of b2, with a modulus at the numerator. Okay. In the first paragraph, the last sentence in the first paragraph, it says for two lines which are perpendicular to each other, then of course the angle between the two lines is a right angle. Right? And we only need to do much more computation when the angle is not 90 degrees. If the angle is 90 degrees, the dot product is 0, then you can straight away say that the angle between the line is a right angle. It's only when the angle is not a right angle, then we have more computation to do. Okay. Right, the final note down here, the scalar product b1 dot b2 may be positive, negative, or 0. We use the modulus sign at the numerator to ensure that the angle theta obtained is an acute angle. Right, that's why the formula is a little bit different from what we learned earlier when we find angle between two vectors. Because this time we want to ensure that the answer that we get is acute. Because for two lines, it's always possible to get two angles between them. One of which is acute, the other is obtuse. And we always take the acute angle as a final answer. We never take the obtuse one when we talk about angle between two lines. Can we use this formula for what we learned earlier? Okay, so to clarify, to avoid confusion, right? If I give you two vectors, let's call it P and Q. If they ask for angle between vectors P and Q, if this answer happened to be 120 degrees, which is obtuse, you would leave your answer as 120. If you write 60 degrees, it will be wrong. Which means when you compute this angle, let's say this is your theta, you would write cos theta to be P dot Q divided by modulus P modulus Q without modulus at the numerator. Without modulus. Okay, so you cannot put the modulus there. If they ask for angle between vectors P and Q, you cannot put modulus there. Okay, same goes for the case like, for example, you have a triangle. You have a triangle in some diagram. Let's say this is A, this is B, this is C. Okay, let's say they want to find this angle theta here. Which from the diagram you see is obvious. Even if you don't have the diagram, if they ask for angle ABC, you take cos of angle ABC equals to BA dot BC divided by length of BA followed by length of BC. Okay, if at the end your angle ABC happen to be obtuse, we will just leave it. Just leave it. Okay, how do we know when it's obtuse whether or not you need to convert to acute? It's based on the question, based on the situation. Okay, so Whatever that we have covered so far, this is the first occasion. Angle between two lines is the first occasion that we have, for the things that we have covered so far. Angle between two lines is the first occasion that requires the angle to be acute. Whatever that we have learned before today, you don't need modulus. Why we need modulus is because it's defined to be acute angle. Angle between two lines is defined to be acute. It must be acute. They force it to be acute. That's why you need a modulus, because you are forced to have an acute answer for angle between two lines. Okay. So take note of the difference. Angle between two lines must be acute. Okay. And by the word line, what I mean is 3D line with infinite line. Must be acute. Okay. But if they give you fixed points, if they say this is point A, this is point B, this is point C, if they ask for angle ABC, if the angle ABC is obtuse, right? If the angle ABC is, let's say, 110 degrees, then it must be written as 110 degree. You can't write it as 70. Right? Because the angle ABC is obtuse. So be very clear when modulus is needed or not. Modulus is only needed when they ask for angle between two lines, because based on the definition, it's always acute. Okay. So first of all, why people want to define angle between two lines to be acute? Consider two intersecting lines. Whether it's 2D or 3D, it's the same idea. L1 and L2. If these are two intersecting lines, you can get angle alpha or angle theta as the angle between the two lines. So to avoid ambiguity, people want to standardize things. So we always take the smaller one. Okay. Since there are two valid answers, we take the smaller one, and people have standardized this. Okay. However, for the case when you have ABC being fixed point, there is no ambiguity what angle to take. Angle ABC, there's only one answer. There's no second possibility. This one, there's no second possibility. That's why you don't have to force it to be acute. And also, if you have two vectors, just like the case of P and Q, P and Q have their direction fixed already. So you can always place them such that they are diverging. So if this angle is obtuse, just leave it there, because there's no second possibility. Angle between P and Q, if it is obtuse, it is obtuse. There's nothing you can do about it. This is different from the case of two lines. Because L1 and L2, there is an argument. I can take alpha as an angle. I can also take theta as an angle. That's why people want to standardize and force it to be acute. Okay. Right. So the formula for angle between two lines, it is applicable. The same formula is applicable for intersecting lines and also for skew lines. The same formula is applicable. So as long as you are clear, when you are forced to have an acute answer, then you would know when you need the modulus at the numerator when you apply the formula. Only when you are forced to have an acute answer, then only you put a modulus at the numerator. Right, the purpose of putting modulus at the numerator is to ensure that you get an acute answer. Next is distance between two parallel lines. So in the diagram above, you see you have two parallel lines. Of course, it only makes sense to ask for the distance when there are two separate parallel lines. This one is, of course, two distinct parallel lines. If the lines are overlapping, then it doesn't make sense to find distance between them. Okay, so this must be distance between two distinct parallel lines. Okay. Now, in the diagram, we can see these are a pair of parallel lines. We call L1 and L2, and A1 and A2, they are the fixed points on the line, which you can read from the line equation. Usually for this kind of question, the line equation will be given. To answer Kushagra's question in chat, Kushagra was asking, is there any way we can use cos 180 minus theta with a modulus equals to cos theta in case you forget the move? I don't really get what you're asking there. Like for the case when you are asked to find angle between two lines, and let's say you are given L1 and L2, and after your computation, let's say you first let theta to be angle between the two lines, between L1 and L2. Then you take cos theta equals to B1 dot B2 divided by B1 dot B2. If you forget the modulus, then at the end, you get, let's say, theta equals to 110 degrees. The best way to fix this is to redo the whole thing. Put the modulus there, then you will get 70 degrees. The best way to fix this is to redo the whole thing. If you don't redo the whole thing, then how are you going to continue? Because you have already defined theta to be the angle between the two lines, and you get theta equals to 110, and you cannot suddenly say theta equals to 180 minus 110, because this is a contradiction. You can't say this. And so the best way is to redo the whole thing. And of course, the best thing is you don't forget. Yeah, why would you want to forget in the first place? Right? And even if you forget, I've told you what is the way to fix it. It's just to redo the whole thing. And with the modulus being added. Okay. Now let's carry on with this distance between two parallel lines. Okay, A1 and A2, they are points on L1 and L2 respectively, which you can read from the line equation. Now, let's say I have my L1 and L2 like this. And here's my point A1, here's my point A2. Now, the distance between the parallel lines is the distance measured when I draw a line that is perpendicular to both L1 and L2. So the green colored distance here, will be the distance between the two parallel lines. And this distance is consistent. And no matter which pair of points you choose along the two lines L1 and L2, as long as it forms a 90 degrees with both of the lines. So if I take a point A1 on L1, and I get the foot of a perpendicular, let's call it F1 here. Distance from A1 to F1 will be the required distance. Okay. So this is equivalent to distance from point to line. It's just distance from point A1 to line L2. And equivalently, I can also regard it this way. I can also make use of my point A2. If this is L2, this is L1. I can measure the distance, let's call it F2 over here, where F2 is a foot of perpendicular from A2 to L1. Then if I erase the line L2, then it's clear that the required distance is just the perpendicular distance from point A2 to line L1. Alright, so if you have this kind of understanding, it will be easy to find distance between two parallel lines. It's just the distance from a point on the first line to the second line. Or the point on the second line towards the first line. And then you can follow the procedure stated on page 11. Wait, now example 15. Wait, find acute angle between the lines with these two equations. The angle between two lines, and in fact, most of the time, in many of the exam questions that ask for angle between two lines, they are going to mention the word acute. Right, so if they mention the word acute, then it's actually reminding you that they force your answer to be acute, which means you need a modulus at the numerator. Once you see the word acute, you are already reminded. You are already reminded that you need modulus at the numerator. And when you apply the formula for cos theta. And so just don't forget the modulus when it is required. Right? So first of all, you need to introduce your theta. If you write cos theta equals to whatever straight away and you write theta equal to something at the end without telling people what theta is, you can't expect people to know. So it is a must to introduce what your theta refers to. Let theta be the acute angle between the lines, between the two lines. Then you apply the formula for cos theta. With modulus at the top, you are taking dot product of the direction vectors, then followed by dividing by their lengths. At the top, you need to sum up three numbers. At the bottom, it is cert 62, cert 5. Which is positive 1 after applying the modulus divided by square root of 310. Then solve for theta. You will get 86.7 degrees to 1 dp. And done. We have 2 more pages to go in this chapter. We still have a bit of time. I think we can start a little bit of example 16. And maybe I just tell you the idea first. Example 16, you are given two lines with the equations. Point A and point B have coordinates 0, 3, 1 and 1, 0, 2, and they expect you to be able to observe that 0, 3, 1 appears here. So this means this is actually point A, and this is actually point B. Right, find the shortest distance between the lines L1 and L2. Okay, for information later in the FP1 syllabus for vectors, you are going to learn shortest distance between two skew lines. You will learn shortest distance between two skew lines. Uh, that is in FP1 syllabus. Okay, so in this P3 syllabus, we only learn shortest distance between two parallel lines. Okay. Now, if such kind of question appears in the exam, they expect you to realize that these two yellow colored vectors are parallel. They expect you to realize that these two are actually parallel. Okay, and you need to show a little bit of working to claim that they are parallel. Then only you use the method described on page 19 just now to find the distance between the lines L1 and L2. And so you will need one or two lines of working to show that the two lines are parallel first. Then only you do your computation. Okay. Right, the time is almost 12 o'clock. I think I will just stop here and I will continue with this example 16 tomorrow. If you have time, I suggest you to attempt it on your own. Then tomorrow when I discuss, you can compare. Right. Okay, I think that's all for today. Yeah, we'll continue tomorrow with example 16. Thank you, everyone. You may leave the video meeting.
Thank you,
Thank you, sir.
sir.
Have a
Thank
nice
you,
Thank you,
day.
sir.
sir. Bye, sir.